Alright, this is the video for 10.8. This is about effusion and diffusion. And again, this is something that we went over last year, so hopefully it should be a little bit of a review. We're going to start off with diffusion. Okay, and diffusion is the idea of gases that are mixing. So you want to think about if I light a candle, okay, and it's scented, that scent is going to slowly leak throughout the entire room. And everybody will slowly smell that. Okay, that is diffusion, where the gases mix. Okay, with diffusion, okay, heavier gases diffuse slower because they're going to bump into one another a lot more often. Also, gas molecules that are larger in size, so stretched out more, okay, those will also bump into one another more often, and those are going to move more slowly. So that is diffusion, okay? Effusion, on the other hand, okay, is where you're looking at a gas passing through a tiny opening in a chamber or container. All right, and like the picture over here on the right, that's where I have a gas, a bunch of gas molecules there on the top. We have a hole here in the middle, and these gas molecules slowly leak through. That is called effusion. Think like air leaking out of a tire. All right, the rate of effusion, okay, is inversely related to the molar mass. This means that the heavier they are, okay, the slower they're going to move again, and the slower they are going to pass through that little tiny opening. All right, it also works then with the faster the velocity, the faster they effuse. And we have an equation that we looked at last year for the rate of effusion. And we have the rate of effusion or diffusion, either one, for gas 1 compared to the rate of effusion or diffusion, again for 2, is equal to the square root of the molar mass of 2 over the molar mass of 1. And again, we did this last year. It's inversely related, and it's also a square root related. Okay. The last thing here is what we call a mean free path. And the mean free path is the average distance traveled by a molecule between collisions. Okay, and this varies with pressure. All right, if I have a higher pressure, that means that it's going to be more crowded because they're going to be colliding more. And if they are more crowded, that means you're going to have a shorter mean-free path. All right, if I have a lower pressure, that means it's going to be more empty, which means it's going to be a longer mean-free path. Okay, and that's just, again, the distance that it travels. So if you go out in the hallway in between periods, okay, and you try and walk around, you have a very short mean-free path before you bump into somebody else. If you go out in the hallway during class time period, that's going to be a much longer mean-free path. There are less people that you're going to bump into and run into. Okay, so let's try the first problem here that deals with the rates of effusion. So it says calculate the ratio of the effusion rates of hydrogen gas and uranium hexafluoride, a gas that's used in the enrichment process to produce fuel for nuclear reactors. So we want to know the ratio, okay, of the rate of effusion of H2 compared to the rate of effusion of uranium, U, hexafluoride, F6. Okay, so if I want a ratio here, that means I'm looking at the rate of this compared to the rate of that. Since I don't know the ratio, I'm just going to figure out the numbers here. And so I've got the molar mass equal to, and they are flipped. So I want the molar mass of H2 on the bottom, which is 2.02, compared to the molar mass of UF6, okay, which is 238 plus 6 times fluorine, which is 19. And what we get is we get 13.2. Okay, so that means 13.2 to 1. So hydrogen is 13 times faster than uranium hexafluoride, which makes sense because it is a lot lighter. Okay, in this next problem, all right, I have an unknown gas that's composed of homonuclear diatomic molecules. Okay, that means the same nucleus, okay, diatomic being two of the same thing. Okay, and it effuses at a rate that is only 0.355 times that of oxygen at the same temperature. What is the identity of the unknown gas? So it's 0.355 times that of oxygen, which means that it should be a lot heavier than O2. It's a lot slower. Okay, this number is less than 1. There's the square root. Okay, and I have my unknown on the bottom here that I don't know. O2 is 32. To get rid of my square root, I'm going to square both sides. So I'm going to have 0.355 squared is equal to 32 over x. I'm going to cross multiply and divide, and I get x being 253.9 grams per mole. Now how do I know what it is? Okay, it's the same thing and it's diatomic. Okay, meaning there's two of them. So 253.9 divided by 2, you will notice that this is iodine. This is I2.